All right, in this lesson we're going to talk about composition of functions. So let's take a look. So our learning target is to refresh our memories a little bit about what functions are and then talk about composition of functions. All right, so we're going to just start off by getting our brains going a little bit and see if you can solve this number puzzle. All right, into functions. What is composition of functions? Before we get into that, we're going to first talk about what a function is. So a function is a special relationship where each x value has exactly one y value. And so let's take a look at what that means. So here I have a couple of sets of ordered pairs. And you can see in the first one, it's a function. Let's just examine our x values. You'll notice this is our domain. Our domain, each x only goes to one y value. Each one has its own y value, okay? Now, in the second one, I've got this, -4, -1, 5, and then I got another -1. So these two right here that's the same x value, and you'll notice they go to a different y value. So this x value, -1, actually has two different y values here and here, namely 7 and -2. So it goes to two different values, so that makes it not a function. Another way to look at this when you're evaluating a table or just a set of ordered pairs is if the x values repeat, it's not a function. So that's kind of a shortcut to look at it. So, okay, so let's look at these right here and see if we can figure out if they're functions or not. Okay, this first one is, if we just take a look at our x's, we have -4, -3, -2, 1, and -3. And we notice that -3 goes to two different y values, so this is no. Okay, how about the second one? I've got 5, 3, 2, 0, and -1. None of those repeat, so they each have their own distinct y value. All of the x values could go to the same y value. So even if all of these y's were the same number, that would be okay. So we're really looking at our x's to see if it goes to two different y's. So this one would also be no, and this would be yes. All right. Here's a mapping diagram. You maybe remember these from your algebra days. So are these functions? This first one is yes. We'll notice these are the easiest way kind of to tell if it's a function. Notice all of these are each arrow coming off of the x values. There's only one arrow, so that's a function. This second one, the -1 here, has two different values that it's going to, so it is not a function. It goes to two different y values. Okay, so there's a couple of things. You also have graphs, and the easiest way to tell from a graph if it's a function or not is to use the vertical line test. So on the left, I have here a picture that's a function, it says, and on the right, I have one that's not a function. And let's examine why that is. So you should be able to draw a vertical line anywhere on the graph, and it should only pass through the graph only once. So you'll notice if I draw a vertical line here, it just passes through once. If I draw another vertical line just once, I should not be able to find any spot where it goes through more than once. So yes, this is a function. No matter where I draw a vertical line, we're good. This one, on the other hand, I can see it goes through the graph here and here, and I can find multiple spots where that's not the case, but you just need really one, okay? So that first one is a function, that second one not a function. Okay, so then take a look at these and see if you can figure out if these are functions or not. All right, this first one is, yes, it's a function. The second one is no, because of right here. This is also no. I can find a vertical line. And this one will be yes. Okay. And then function notation, just remember function notation is f of x is equal to 5x plus 7. That really means the same thing as f of x is the same as y. It's just called function notation. This just means really this, okay? It's just another way to say that. So what would be the purpose of that? Well, if you have a bunch of functions like these, it's easier to identify which one's which by just saying, hey, I want you to look at the h of x function. Well, if I have it labeled this way, it's easier to know that that's really what this means, okay? Rather than having to say the whole thing. So it's just a shortcut, and this is handy as we get into bigger functions that get larger and larger. So that's kind of why we use it. That's one of the reasons. Okay, and then to review how we evaluate functions, if I have a function, for example, that says g of x is equal to 5x squared plus 3x minus 2, and they say to find g of negative 2. Well, in our original here, we have an x, and now we're replacing that x with negative 2. So that same thing applies when you plug it in. You're going to replace all of the x's in this function with negative 2, which is what I did here. And then simplified, and then I have 12. And again, another nice thing about function notation is now I have my answer, which is my output, but I also have what I plugged in. So I know that actually when x is negative 2, y is 12. So it's kind of nice because this tells me both what x was to plug in and what the output is, 12. Okay? All right, so now that we've reviewed functions, let's talk about composition of functions. And composition of functions is really two functions where you use the output from one function as the input for a second function. That sounds a little weird, but this right here is read f of g of x. So, and the way that we work these is we start from the inside right here and we work our way out, okay? And you'll see what I mean here by this in a second. So we're gonna use these two functions here for this example. It says if f of x is equal to x squared minus 1 and g of x is equal to 3x, then the first thing we need to find is f of g of x. Then we're also going to find g of f of x. Okay, so let's see if we can do this. Kind of zoom in here a little bit. So we're going to start by saying, all right, I see g of x, and I know that g of x is 3x. So really all I'm going to do is start by working inside and then going out. So I'm going to replace g of x with 3x. The output for that first function, g of x, is 3x. And we're going to now use that as the input for this function. Okay? So now I'm going to just look at just f of x. And wherever I see an x in that function, we're going to replace it with 3x. So instead of x squared, I'm going to put 3x in parentheses squared minus 1. And then I just simplify this. Okay, well 3x squared, that means 3x times 3x. So that's 9x squared minus 1. So f of g of x is equal to 9x squared minus 1. And there's that answer. Okay, kind of weird. Let's see if maybe we can try another one and hopefully this will make some sense. Okay, so really this second one we're just going backwards. This one says find g of f of x. So now, I guess I'll move over a little bit so you can see this whole thing. So now again, start on the inside and replace that. So the output of f of x is this right here. So we're just going to start by writing g of, and then what is f of x? It's x squared minus 1. Okay, so now that we've done that, now we're just going to look at just this function. And it says g of x is equal to 3x. So wherever I see an x in that function, I'm going to replace it now with x squared minus 1. Okay, so equals 3, place of x, I'm going to put x squared minus 1. I'm kind of running out of room there. All right, and now I'm going to simplify that function. So that would be distribute the 3, we get 3x squared minus 3. So that means g of f of x is equal to 3x squared minus 3. All right, and that is a composition of functions. It's a little weird, but it's taking the output of one function and using it as the input for a second. And remember to start on the inside and work your way out. That will be the easiest way to go. Okay, oh, I guess I left myself a little extra room. And then when you finish that, you can start working on the composition of functions worksheet. You'll need probably MCA calculator, Notability, your iPad, obviously, your notes, and Schoology. All right, have a good one. See you later.